In the year 1925, Einstein shared with a student his burning desire to understand the universe. "I want to know how God created this world," he said as they strolled along. "I'm not interested in this or that phenomenon, in the spectrum of this or that element. I want to know his thoughts. The rest are just details." This one conversation expresses the core of Einstein's guiding principle, one that has driven humanity to inquire, discover, experiment, and most importantly, learn about this universe we call home. But what was Einstein really talking about? And can human knowledge ever reach a point where we understand everything? Since the discovery of the world of quantum mechanics in the early 20th century, scientists have been racking their brain trying to understand how it works. Even a century later, we're still not sure how and why subatomic particles behave the way they do. But that's just half the problem. The discovery of quantum theory posed a more serious issue that Einstein, Stephen Hawking, and other world-renowned physicists have been working tirelessly to solve. That challenge can be summarized in one word: unification. You see, modern physics is split into two pillars: classical physics, the physics of Newton, Einstein, and Galileo, which predicts gravity and describes the motion of massive things in our cosmos like stars and planets, and quantum physics, which governs the world of subatomic particles according to its own set of laws and rules. Both pillars describe their respective worlds accurately, but fail when applied to each other's subject matter. Einstein's preoccupation was that there must be a way that these two worlds could reconcile. There has to be a theory that unifies the world of the subatomic with the world of the massive. A theory that can predict, well, everything. Now you might be thinking, so why should we care? Well, a unified theory that can bridge both of these worlds could potentially unlock many of our universe's secrets and answer some of the deepest philosophical and theological questions that we've been asking since the days of Galileo. What are we truly made of? What happened before the Big Bang? Are we living in a multiverse? The unified theory, or the theory of everything, might just have the answers to all of these questions. The universe and everything in it is glued together by four fundamental forces. I made an entire video on these four forces, so if you really want to fully understand all of them, I suggest you check it out. But for the sake of this video, here is the gist of what they do. Big objects like stars, planets, humans, and cats are all governed by the force of gravity. And thanks to Einstein and his general theory of relativity, we now know that gravity isn't a force that magically pulls objects together. Instead, it's the curving and warping of the fabric of our universe, space-time. While all these big objects are governed by just one fundamental force, subatomic particles, on the other hand, are governed by three fundamental forces, as if they weren't already confusing enough. These three fundamental forces are electromagnetic, weak nuclear, and strong nuclear. Electromagnetism holds atoms together, the strong force holds nuclei together, and the weak force is responsible for some type of nuclear decay. These particles, along with their respective forces, make up what we call the Standard Model. The Standard Model describes the world of the very small. We know that everything in the universe is made of subatomic particles, from planets and stars to humans and dogs. We know that all of these things are made of atoms, and atoms are made of protons, neutrons, and electrons. In the 1960s, we discovered that even protons and neutrons are made of even smaller particles called quarks, and electrons from leptons. Using different combinations of these particles and their respective forces, we can build atoms, molecules, humans, planets, and even stars. So it seems that the Standard Model is a comprehensive interpretation of our universe. But it doesn't include everything. The truth is, finding the smallest subatomic particles is only the first step to getting to a theory of everything. The second step would be finding a place for gravity in this model. There are two reasons why gravity isn't included. The first is that when it comes to small particles, the force of gravity is so weak that it doesn't have any effect on a quantum system. The second reason is that we don't really know how to incorporate general relativity, which describes the motion of large objects, into the world of quantum that governs subatomic particles. Many great minds, including Einstein, tried tirelessly. It's said that even on his deathbed, Einstein revisited his notes on the theory of everything and tried one last time to find an elegant solution to explain the fundamental differences between the world of the small and that of the large. But unfortunately, he ran out of time. So that's that, right? While we still haven't found a theory that can explain everything, we have made significant progress, and maybe the most groundbreaking was that of another brilliant mind, Stephen Hawking. In 2014, a movie was made on the impactful life of Stephen Hawking. As a result, Hawking became one of the most revered physicists in the world, and one of the most admired by pop culture. Away from the limelight, however, Hawking, like Einstein, had an obsessive yearning to understand the universe and never ceased to challenge our knowledge of it. One of his greatest contributions was the discovery of what is now known as Hawking radiation. In 1974, Hawking discovered one of the biggest breakthroughs of the 20th century, a groundbreaking interpretation of black holes, as well as an unprecedented interaction between the world of quantum and gravity. Hawking's discovery was so ingenious that it gave us hope that the theory of everything, the holy grail of physics, is still a human possibility. Black holes are densely packed regions of space where the gravitational pull is so strong that nothing can escape, not even light. Einstein predicted the presence of black holes through his general theory of relativity in 1916, and we confirmed his predictions in 1974 when we observed our first black hole in the Milky Way. In the same year, Hawking discovered that black holes are like a vitamin tablet placed in water. They can dissipate in time and release energy. This is what we know as Hawking radiation today. But how can energy escape a black hole when nothing else can? Hawking used a quantum understanding to explain this. When we think of space, we imagine large, cold, empty places, but in reality, space is alive with the active creation and destruction of energy at the subatomic stage. Particles are created in pairs, matter and antimatter, and they are constantly created and destroyed in a concept known as annihilation. Hawking imagined a pair of particles created very close to the event horizon of a black hole. This is the boundary around a black hole from which nothing can escape. He then showed that these particles don't need to annihilate each other, since one of them can be sucked into the black hole. If the black hole is receiving negative energy, then it has to release energy in order for the law of conservation of energy to hold. Hawking also proved that black holes lose mass with time, and they don't last forever. But more importantly, he was able to arrive at this discovery by merging a quantum principle with the concept of gravity. This is by far the closest we've come to a theory of everything, a unified field theory, or quantum gravity. But as with most things in science, the fact that we haven't found that one elegant equation does not mean that we have failed. In fact, maybe the real treasure was the discoveries we made along the way, many of which have paved the way for a brighter future for humankind. String theory is one of the most prominent ones. It suggests that subatomic particles such as electrons and quarks are made of tiny vibrating strings or filaments that twist and fold, creating everything in our universe. Just like the strings of a violin, they can vibrate in various patterns, creating different kinds of particles, including the graviton, a hypothetical particle that, according to quantum mechanics, should carry the force of gravity. On paper, string theory could unite gravity and quantum mechanics under one framework once and for all. The theory was popularized in the 60s and 70s, and its mathematics predicts small bundled up extra dimensions that give rise to a network of universes, or a multiverse. While this theory is prominent, it's highly untestable, even with access to the latest technology. String theory, though, is only the beginning. After almost 2 decades of tireless research, we've discovered the Higgs boson. This proved that electrons and quarks inside the atom get their mass from an invisible field that spreads throughout space. The discovery took an effort from a group of 3,000 scientists that dedicated endless hours to the cause that would surely bring our species one step closer to understanding our universe. We've also discovered that all the atoms and light in the universe only make up less than 5% of the total content of the cosmos. The remaining 95% is composed of dark matter and dark energy, which are invisible, but whose effects dominate the evolution of our universe. Dark matter provides the gravitational pull that keeps galaxies together, while dark energy is responsible for the ever-accelerating expansion of our universe. For thousands of years, we've looked to the heavens and wondered what mysteries are hiding beyond the clouds. Since 1970, there have been more than 90 telescopes placed in orbit by NASA and the ESA to bring the universe closer to us. And with the James Webb Telescope that launched on December 25, 2021, we entered a new era of discovery. This telescope is the largest and most powerful one ever built, and its daunting task is to find the first galaxies that formed in the early universe, and peer through dusty clouds to see stars forming planetary systems. We may not have found the theory that unites quantum with gravity yet, but every discovery brings us one step closer to that ultimate goal of unification. Throughout our time on this planet, we've pushed the boundaries of existence by asking tough questions and working tirelessly to find the answers. Our species has been defined by its incessant thirst for knowledge and unwavering hope in a unified universe. 350 years have elapsed since our first big successful step in this journey, when Newton unified the heavens with the earth, revealing that planets, stars, and apples are guided by the same set of laws. 200 years later, James Clerk Maxwell coupled electricity with magnetism, and then Einstein linked space and time and warped them into one fabric that we now know as space-time. Looking at the timeline of these events, it shouldn't be surprising that the road ahead could be much longer. Einstein died dreaming of a physical world governed by one set of laws, a unified framework that can unlock the mysteries of our universe, and Hawking never ceased to look up at the stars and wonder what mysteries lie ahead waiting to be found. Whether the theory of everything is a realistic quest or a delusional attempt to make sense of the absurdity of the universe, one thing is certain. Our unwavering hope in the search for unification will only lead to humanity's advancement as a species. If you feel you're in a black hole, don't give up. There's a way out. Today's video was sponsored by MyHeritage. MyHeritage is the leading global service for family history research and DNA testing. Trusted by 90 million users, MyHeritage not only makes building your family tree a simple and enjoyable activity, it also gives you access to powerful tools that can help you research your family history and grow your tree. MyHeritage is home to more than 18 billion easily searchable historical records, as well as advanced AI technologies for repairing, enhancing, colorizing, and animating your precious historical photos. While researching the theory of everything and thinking about humanity's future, I couldn't help but also think about our past, where we came from and how we got here. This search pushed me to find information about my family history using MyHeritage. The information I found was so good that I had to make all my friends grow their family tree as well, and Anna Maria's story is the most fascinating of all. With MyHeritage, she was able to discover that her maternal grandmother's mother is a Bernardo, the same Bernardo that's a well-known international pasta brand. Some of her family members also used the site, and so she was able to find photos of her maternal grandparents whom she'd never seen before. As if that wasn't fascinating enough, she was also able to track down her family lineage by 500 years, after which she's discovered that there's a duke in her family. Anna Maria lives in Canada, but she was able to find extended family members in both Italy and Argentina. She even found a cousin who moved from Argentina to Canada, and so she was able to organize a little family reunion with her sister, father, her cousin, and his dad. Next, Anna Maria is headed to Argentina and Italy to visit the rest of her family, all from one quick search on MyHeritage. So, if you would like to find out more about your family history, right now, you can sign up for a 14-day free trial and enjoy all the amazing features MyHeritage has to offer. And if you decide to continue your subscription, you also get a 50% discount if you use the link in the description. And who knows, you might also be planning a trip around the world soon.